Today's topic is arc flash and the mitigation techniques involved in it, causes of arc flash, the current standards, the safety techniques that I'd like to see y'all follow, arc flash mitigation, which includes the space and distance, which is the 1584 standards, the arc res switchgear, which obviously we make, and different types of relays, primarily the optical relay, which is the REA. Firstly, what is an arc flash? You know, everybody talks about arc flash, everybody talks about the difficulties associated with arc flash, how do we solve the problem, but really what is an arc flash? And first of all, you got to relate that the temperature of the sun, as seen here, is 5,000 degrees C. Well, if you think of that as one point in a universe and suddenly it appears, i.e. in switchgear, this is what is occurring. And because there's so much heat in one spot in such a short period of time, you end up with a volumetric expansion of the air that is around it, all the material that is around it. In effect, you have a rapid release, as the slide depicts, of the pressure that's associated with this heat. Okay? So if you look at this element right here, you can see that we're at almost 5 times the temperature of the sun. This gets really hot really fast, and it makes for very dangerous circumstances. Also, the other part of this is the light intensity, which is operable from the perspective of how an optical relay functions in terms of mitigating that the arc flash and the resultant arc pressure that is exerted. This is why everybody's concerned, is because you have 40,000 volumetric pressures that are exhibited. Let me give you an example of that. When we started testing arc-resistant switchgear back in '94, we discovered that we had about 13 pounds per square inch on the doors and sides walls of a frame of switchgear. This was at 31.5 Ka. We just finished testing at 63 Ka, and we discovered that, lo and behold, we thought this was a nice lineal curve. Well, we discovered that it isn't lineal at all. It is exponential. We ended up with almost a PSI of 30 PSI. What that translates to almost 7,000 pounds on the door. And all of that occurring in the first 3 to 5 cycles of the arcing incident. Why is that important? It's important because I can tell you that in that type of design, the door that is in front of the breaker compartment, for instance, weighs about 330 pounds. A door in front of a typical non-arc resistant switchgear is going to weigh about 30 pounds. A door for a 25 Ka lineup of switchgear is going to weigh about 160 pounds. So you can see the progression of the weight and the amount of steel that are involved as the Ka goes up. And that's exactly where today's systems are going. You know, this wouldn't be near as alarming if we were able to keep, as we did many years ago, 500, the old 500 MVA rule. Well, that no longer is true. I mean, for instance, I know for a fact that in the world of Con Ed, I mean, they buy 63 Ka gear as a typical run-of-the-mill switchgear. Many, many other utilities are going that route. Certainly the petrochem business is going that route. So what does this tell you? It tells you that the systems are increasing at an incredible rate because the strength and the combination of the transformers that we're putting in, the loads that we're trying to feed, are so large today. And they are forecasted to do nothing but get larger as time goes forward. Okay, so let's talk about when arcing incidents typically occur. All right, the one that I want you all to recognize is that typically when an arcing incident occurs, it occurs 65% with somebody working on the switchgear. All right, this is the most alarming statistic that we were able to determine. And why is it alarming? Because that's when the person is involved in the gear. And what's he doing? You know, they're messing around with the relays, they're maintaining the electronic low voltage control, or they're maintaining the breaker. That's, or racking out PT compartments. You know, this is very typical of what happens when you're maintaining metal-clad switchgear. And it occurs because where is the single biggest point that an arc can occur? As you're racking the device in or out of the cell. That's really when it occurs. The other incident, which is without the operator and the operator in front of a close, which is 35%, occurs basically in the rear of the switchgear, in the cable compartment. Almost 90% of all switchgear failures occur in the cable compartment, and they occur at the stress cone. And you say, why? Well, if you think about it, what's the one element that we as a manufacturer cannot control? It is the person that's making up that stress cone. We cannot control the consistency. We cannot control the degree of craftsmanship that that individual has. None of those things we can control. And for the most part, neither can most management people within a utility or an industrial plant. All right, so that one aspect of it, as time goes forward, a failure will occur at the stress cone point, or bolts will become loose, then they rattle around. You end up with heat. Heat then decays the copper. When that occurs, then you end up with arcing, and all of a sudden, boom, everything goes up. Okay, what happens when that occurs? Several things. There's shrapnel, there's pressure wave, hot gases, fumes, and molten metal. Taken together, guess which one is the worst case? And it's going to become perhaps a surprise to some of you. Actually, it's this. People talk about the pressure wave. Yeah, that'll kill you. The shrapnel will kill you. But what really occurs, even in a degree 2 safe gear, when unless all the flaps close correctly, the gases are what are so devastating. Why? Because everything, remember the extreme heat I was talking about? Well, you got copper, you've got plastics, you've got all kinds of polymers, steel, paint, everything is vaporizing at an incredible rate. That combination of molten and gaseous plume that is occurring within the switchgear suddenly ends up as a concentrated gas. That gas then becomes a toxic agent. It rolls out at the same time that the rest of the switchgear is going up in smoke, okay? Without a plenum, without arc-resistant switchgear, that gas is going to be all over the place in front of the gear. Yeah, so the guy may be suited up in, say, a PPE 4, we'll say. And that will keep him from being burned. All right, but the pressure wave, I will guarantee, will blow him 15 feet backwards. And if that doesn't get him, all the gases around him that are permeating the air will equally get him. So that's why when we talk about what occurs in an arc during the event, this is why we have to take all of them as a combination, okay? All right, the causes, and I touched on some of them already, but human error, I think, is one of the biggest issues. Why? Because as some maintenance people are racking in breakers, for instance, they will try to what we call over torque the racking screw. When that occurs, the breaker has a tendency to jump, all right, or it has a tendency to compress and crush. Bad things happen, okay? This is what I call a human error. It also is our fault as manufacturers, quite honestly. You know, we should come up with a more foolproof racking system. Well, in response to that, we came up with remote racking, okay, which I'm going to discuss a little bit. But those are the kinds of things that all of us need to be aware of, all right? In mechanical failure, you know, you have loose connections. You have, you know, all breakers, like mechanical devices, inherently can fail. Do they always fail? No. but they certainly can fail. And I'm going to talk about a breaker in a while that addresses this issue from a reliability standpoint. The intrusion of snakes, mice, rat, other vermin, they occur in switchgear. In non-arc resistant switchgear, there's typically the cable entrance area is wide open. All right, so all of this vermin can come up and they get inside and explosions occur in the cable compartment. All right, in arc resistant switchgear, you don't have that because everything is sealed. It must be sealed, otherwise you don't have arc resistant switchgear. You know, many customers think that all they got to do is train normal cables down into the cable way or cable pit and they're done. In arc res switchgear, you can't do that. You've got to put in gland seals on each of those cables to maintain the integrity of the cabinet itself. And then lastly, you have environmental. This is when coal dust and other types of environmental dust particles in the air will land on buses and contaminate them. Near the seashore, obviously you have salt in the air. All of those have a debilitating effect on the switchgear itself. Okay, so taken as a total, you can see there's a lot of things that can and unfortunately do go wrong with metal clad gear. Statistically, this is what we found. We went to the insurance industry and said, okay, how many people are you know, let's try to quantify what we're really dealing with. And we discovered that 5 to 10 people per day go to burn centers to be treated for burns from an electrical you know, short circuit or whatever it may have occurred. Okay, this is 2,000, you know, roughly 2,000 to 3,000 people a year. This is a lot of people. You know, the other alarming statistic is this one. A very large utility in the Midwest ran a study on this, and they found that every 18 months they had a fatality due to electrical issues. Let's talk a little bit about where the standards, today's standards, came from. They came primarily from Europe. And why Europe? Well, Europe, unfortunately, in the IEC design of switchgear, they used buses, primarily, you know, the main bus, without bus supports between the frames. This has been universally true in Europe for many, many years. Well, they discovered that over this period of time, lo and behold, if you had a bus fault, it would tend to move right down the busway. So you would, in effect, envelop every frame within the switchgear as it goes down, as it went down the lineup of switchgear. What this did was cause a catastrophic failure, not a single failure, but a catastrophic failure of virtually all the frames within a switchgear lineup. So it led to many deaths. And the European community said, well, enough of this. You know, how are we going to fix this? And the folks at ABB, Siemens, Maryland-Geron, others in the European world got together at the IEC level and developed the arc-resistant standards that the Europeans have gone forward with. There's a world of difference, incidentally, between how IEC approaches arc-resistant standards and how we do it in the United States. And perhaps I'll talk a little bit about it later. But in '87, our brethren to the north of us, up in Canada, said this is a good idea. So they brought over the same concept but tried to apply it to the ANSI world, because the CSA standards are very similar to the ANSI standards. In fact, as some would say, they're identical. What occurs is that when the Canadian put it together, they did it under the guise of the EMAC standards organization, which now doesn't exist, but at the time it did. And they came up with these three classifications, A, B, and C. Virtually no one buys arc-resistant construction in the front only. And that's pretty obvious. I mean, why would you only do it in the front when you should be doing it, you know, people walk around switchgear all the time. So B became more of the standard, if you will, designed for Canada. And that's front, rear, and sides. Then you have type C, which was front, rear, and sides. and isolation between the different compartments. Well, when ANSI took over this task of trying to move a standard into the United States in 2001, we looked at it and said, I know what we'll do. We're going to go this thing a little bit differently. Number one was we looked at the three standards, or these three classifications, all right. But we said, wait a minute. The whole concept that EMAC started with was they would allow the effluent from an arcing incident to blow out the roof of the switchgear. Well, it made things relatively easy to install it. It complicated the world greatly because what goes up must come down. These hot particles that we're talking about from molten copper and steel literally were being expelled out the top, and they were falling back down on people, and lots of people were getting hurt. So we, at the ANSI subcommittee, we decided, at C37, we decided, we're not going to do that. We're going to put a requirement that you put test strips all the way around the top of the switchgear. This, in effect, created the need and the requirement for putting a plenum on top of all switchgear. And that's where the plenum came from. Okay? B and C, we created 2B. 2B is if I'm in front of the switchgear and I need to work on the low voltage cabinet, whether it be from anybody's switchgear for that matter, different manufacturers adopt different methods of creating a low voltage cabinet. But in our world, we just have a door. We open up the door and we allow the workers obviously to work inside. The issue here is that when you open up that door in normal switchgear, it's just like opening up a breaker door. If you have an incident that occurs inside the switchgear, that same amount of gases and destruction are going to hit you the same way. So in 2B construction, we isolate the low voltage cabinet totally. And what does that mean? It means that we, as manufacturers, had to put in reinforcing behind the rear wall of a low voltage compartment. And this made sense because truly 90% of all work that is done on metal-clad switchgear is really done in that compartment. Very few people actually need to get into the breaker compartment as opposed to resetting relays or low voltage control or whatever it may happen to be. Okay? So that's why 2B is becoming virtually the standard in the United States. In other words, when people talk of arc-resistant switchgear, most of the time they're talking about type 2B switchgear. All right, this addresses the personnel side of arc mitigation. What about the switchgear itself? If you recall, there was a type C in the original EMAC logic. In C37 20.7, we developed type 2C. It was Annex 2C. In Annex 2C, we said, okay, we're going to have personnel protection, but we're also going to have sustainability of the switchgear itself. Because it does no good. Yeah, well, it obviously does good for people to be protected, but along with it, we have a whole process, whether it be utility or an industrial. The same thing is true. Either you're trying to spin a meter to gain revenue, or you're trying to save a process to continue building the product or manufacturing the product that you're trying to build. Okay? So what C does is it isolates between each of the compartments. In other words, if a fault should occur in the lower breaker compartment, and say in too high switchgear, and you had an upper breaker, lo and behold, it would not migrate to the upper breaker or a PT compartment next to it. In other words, we isolated the fault to only that compartment that was impacted. This allowed the rest of the switchgear to operate correctly. The drivers in this equation have been for several years now, OSHA 29 and to an extent IEEE 1584, because 1584 gave us all the mathematical background to actually create the calories per centimeter squared, and the barrier distance from the arcing point to wherever we were going to have to be. We take that data and we plug it back into a PPE calculation that is done under NFPA 70E. I would also tell you that in doing this, we ended up with this table on the NFPA 70E if you read the whole regulation. This table states that if you're going to be in the cubicle, in the breaker cubicle, you're at level PPE 4. These are generalized requirements that eventually will find their way into the NEC codebook, I might also tell you. It lists the risk and hazard category. Hazard category to NFPA is the PPE rating. All right, it starts at 4, and look at all the zeros. That's what arc-resistant switchgear does. This 2 down here occurred because when this was published in 2009, our buddies at Cutler Hammer didn't have 2B exactly on the street. So NFPA went ahead and decided to list that as category 2 until they got it. Well, they now have it, so now that 2 will become 0. So now we have arc-resistant switchgear that is saying, you open up the door to the breaker compartment, you're in 4. That's a moon suit for y'all that don't understand what 4 is. The rest of it all drops to 0. Okay, safety measures that I perceive that all customers should be taking. All right, we need to understand all of these. These are the 1584 calculations. One of the key elements in here is the clearing time of the breaker itself. Because as I go forward, you'll see very quickly that the lowest amount of time will end up with the lowest amount of arcing energy. And that's critical to reducing the PPE requirement. Other things you can do. There's elimination, substitution, engineering controls, work practices, personnel, well, PPE, training, and communication. These are all hallmarks of any safety program within any industrial or utility for that matter. All of these wrap together, and if you look at the NFPA regulations, you'll find out that all of these are addressed in the NFPA regs, along with the OSHA regs. This is what it ends up as, a warning label. All right, we were asked many times, why can't a manufacturer put a warning label on switchgear? And the obvious answer is, we don't know the application. If we knew all the parameters of the application, hell, we can do the 1584 calculations as well as y'all can. But we can't because we don't know the application. That's why we can't put the labels on the switchgear. Okay? This quadrant slide really addresses a summary of what I just went through. One of the key elements in here about moving people away is the remote racking in today's world. And we'll look a little bit into remote racking in a second. The next one is automatic secondaries. You know, if you go back in time, I mean, since the 1940s, we've always had automatic secondary disconnects. And we created, in effect, the test position. So all switchgear today, you have a disconnect position, you have a test position, you have a connected position. In the IEC world, you only have connected or disconnected, and you have a plug that creates the test. Okay? Doesn't say it's wrong, it just says it's different. Okay? The next one here is if you're talking about non-arc res switchgear, what's the best thing you can do is take the relays off of the switchgear and put them on separate racks somewhere away from the switchgear. And what are we trying to do? We're trying to create a larger barrier distance between the product, i.e. something that's going to be worked on. Remember my analogy to 90% of all work being done in the low voltage compartment? Well, that's what this is all about, the relays and the meters. Let's get them out of the switchgear, put them someplace else. All right, there are also mitigation on retrofit, okay? And let's talk a little bit about that. In retrofitting, there are several things you can do. One, you can put in arc mitigation relays, i.e. the REA, or other relays. I know that Schweitzer has an optical port on their relays, as does ABB. There is what I call a crowbar approach to arc mitigation. In other words, something that is sensing the fault, and then all of a sudden we just close a ground on the main bus and short the entire switchgear out instantaneously, or certainly within the first 3 to 5 cycles. And next year, we will be announcing a completely different type of device that will fulfill the retrofit aspect of this, because one of the things that is holding up the parade in mandating arc-resistant switchgear as part of the general purchasing under C37 20.2, which is the general switchgear specification, is the fact that so many customers think, what do I do about my legacy? You know, I've got, yeah, that's fine, I got arc-res switchgear for all my new stuff. What do I do about the other 300 lineups of switchgear I've got? Well, we're trying to address that, and next year, about this time, we'll have a product we think that will solve that for virtually everybody. Okay, so if you look at what's possible right now, use remote racking. If I encourage you to come by the booth, we have a remote racking unit that we just announced. It has the same logic as most remote racking. I mean, virtually everybody's got one. Ours allows you to pick it up, put it in whatever frame position you're talking about, whether it be upper or lower, PT, CT, it doesn't really matter. And remotely rack the breaker in and out, or the PT compartment in and out, very, very safely from, say, 50 feet away. Okay? The next one is, do specify automatic secondary disconnects, because we've seen some customers that are saying, hey, maybe I ought to be looking at an IEC design. You know, just understand that there are things that are within ANSI that truly do prove to be, over many decades, time-proven logic in terms of what created the safety to begin with. Okay? This is the reason why in the European world they had the problem. And actually here in the US we didn't have the problem, because we always had metal barriers in between the frames. Okay? Yeah.
Wasn't that a requirement at one time? You had to have gas barriers many years ago?
Absolutely. It is. Started in 1948.
I remember.
Yeah. I wasn't there in 40. Well, I was there in 48, but I wasn't active in the industry. Well, we've always had 11 gauge between frames. Always. Okay? In the European world, they never had that requirement. Okay? That's why they would end up with a rolling fault down the bus. Okay. The next item is IR ports. And why do I put that up here as a mitigation? Because if you recall my discussion about the 90% failure of stress cones, this is why. Because if you have an IR port and you're thermally looking at this switchgear on a regular basis, first of all, you're not opening up doors, which is the #1 thing. Never open up the door. So if I have an IR port and I'm looking in there and I see that things are heating up on a particular connection, lo and behold, I can schedule an outage. Because believe me, you're going to have to take the whole switchgear down to look at this particular unit that's having the problem with high heat. Okay? Now let's talk about the one thing that I believe will help all of us understand why we don't want to go into a breaker compartment. If we could avoid going into breaker compartments which have the level 4 PPE, we have eliminated the vast majority of the potential for someone getting hurt. The AMVAC circuit breaker, or any magnetically actuated breaker, we happen to make an AMVAC, is, in my opinion, the way to go. Why? Because it's got 7 moving parts. It rarely does it break. I mean, if you look at the maintenance schedule on this, it has a maintenance schedule between 4 and 6 years. I mean, that extends. Most spring-charged mechanisms have maintenance schedules anywhere between 1 and 3 years. So what have you done? You know, you have reduced by a factor of 2/3 the potential for one of your people getting hurt because they're simply not in the breaker compartment. That's what we're trying to do, is keep people out of the switchgear. In arc res construction, the basic logic is that if a fault is occurring down here in the breaker compartment, it blows through. There's a flap that sits here, and you can see it here. Then it blows up through the top. The same thing is true in the bus compartment. There's normally a flap right here. It blows forward, and the gases go up the top into the plenum. In a cable compartment, they just vent straight to the top. I would encourage you to come on out and look at the demo that I have on the floor, because it very graphically, in fact, as I have a smoke machine and all sorts of things, that show you how the actual flow of gases occur. One of the elements that folks need to recognize about arc-resistant switchgear is that it is designed differently than regular switchgear. All right, when you start laying out a typical switchgear, you're just worrying about stacking breakers and making sure your bus size is right. In arc-res construction, there are a number of issues that need to be addressed. Number one is that I have to have vents. Every X number of frames, I've got to have a way to get those gases up to the plenum. And depending upon whether or not I have 3,000 amp, 2,000 amp breakers in it, the number of those vents that go northward will increase. So there's a whole logic of how you lay out relays, the number of relays, etc., that we have to go through. So I would tell you that the first time you lay out an arc-res switchgear design, I would encourage you to call us. We will be more than happy to walk you through the process of designing the switchgear correctly so that you don't have to redesign the switchgear later. We were talking about the pressure wave a little bit earlier. This is why it's so important. You can see that this is the pressure at 5 milliseconds. This pressure hits this point, and in arc-res switchgear, you notice at this point, what happens? The flaps open, all right? That pressure wave falls like a rock, all right? If this were standard switchgear, the pressure wave continues to build, all right? This is the switchgear rupture curve for steel, and obviously you blow it to smithereens, and that occurs at about 9 milliseconds. So you can see that that's why in standard metal-clad switchgear, things blow up, okay? And this is the reason why it happens. You know, the switchgear steel simply can't handle it. The plenum construction, and I show this inside a PVC because it's important to recognize that one of the design elements, if you're putting metal-clad switchgear, arc-res switchgear inside a building, you have got to allow for the plenum height, okay? Plus, there are see this little box right here? That little box is for 2,000 and 3,000 amp breakers because I have a vent above that so I can let the heat out. All right, but as soon as the heat and an arcing event occurs, that same vent has got to shut down. Well, up on top, there's a shutdown louvering system that stops everything, and I got to have a reset, and that's why this thing continues to go up. Well, what does that mean? It means that the typical distance above a lineup of metal clad will be 3 feet higher than standard metal and clad switchgear. So instead of having, say, a 9-foot building, you're going to have a 12-foot building. Well, this becomes a concern, especially with the pitch of the roof, about getting this thing down the road. You know, there are many highway bridges that are set at 12.5 feet. So we have to watch this very, very carefully, okay, to make sure that we can get this thing down the road. To give you an idea of where we're going relative to the adoption of arc-resistant switchgear, I decided to go ahead and create this slide. All right, this all started back in '95 when at ABB we introduced arc-res switchgear to the marketplace. And obviously we were at 0. All right, then in 2003, almost 9 years later, we were rocking along at a whole 10%. Not a lot of traction here, guys. All right, and we were beginning to question our own sanity. We said, what did we do? Then, lo and behold, I have one more, but long about 2007, several things happened. One, the NFPA and the other governmental regulation people suddenly drafted all the documents that I showed you before. Well, what do you think that did to the market? It's the reason you're here, as they say today, is everybody wanted to know, how do I handle this? Where do I go from here? Well, lo and behold, as time has gone forward, and here we are in 2011, 70% of the switchgear that we see at ABB is arc-resistant switchgear. So do I say with some confidence that in 3 to 5 years we will be building nothing but arc-resistant switchgear? That is an absolute fact. In fact is, I think it's going to occur from our perspective, and as a product manager for this, I'm looking at it very seriously of saying, why am I continuing to build a non-arc resistant product when the market is driving me the opposite direction? Okay? So that's where we're coming from. One of the opportunities that all of us have, whether it be in a non-arc resistant world or in an arc resistant world, is how do we clear these faults faster? And this is the solution. The REA relay optically looks at the light source. This light source is bright enough that we see it and actually cause a trip signal to go out through high-speed contacts in 2.5 milliseconds. If you recall the example I showed you earlier about the pressure wave, that pressure wave is, at 7 to 9. Well, if I just took 2.5 milliseconds to figure out that I got a problem, then if I have a 3-cycle breaker that's a 50 millisecond device, I suddenly now have a 53 millisecond clearing time. What does a 53 millisecond clearing time really mean? As you can see, this green area is defining what the calorie counts are, okay? This tells you just how bad things are. That's why in the red zone, you're in, this thing cuts over at 40 calories per centimeter squared, which tells you got to shut the switchgear down in order to work on it. The green zone says you're in PPE 1, which is pretty light stuff. You can actually work in that. As you go forward, and this Excel spreadsheet is available. Anybody just send me a card or something. I'd be more than happy to send it to you, where you can actually put in your switchgear KV, your KAs, and actually do the work for you. This has got a lot of 1584 formulas embedded in the cells. That's why it's valuable. All right, and you can see that as time goes down, these are the incident energy going out that way. This is the voltage fault current. This way, these are the clearing times, okay, in seconds. All right, so if I'm at 53 milliseconds, I'm way down here in that curve. Well, what that does is it forces all those cells towards that direction. Obviously, if I've got, say, a 50 Ka fault, okay, and if you're clearing at a 1/10, then you're at 7 centimeters per squared, calories per centimeter squared. I didn't get it out. So at this point, you're in PPE 1. Yet, if you're taking 2/10 of a millisecond, or pardon me, 2/10 of a second, then you're suddenly in PPE 2. And it just goes worse and worse and worse as you go down in terms of time. So at 53 milliseconds, which is as fast as I can clear a fault with a 3-cycle breaker and an REA, you're in this range. Well, that says that through 30 Ka, I'm still at PPE level 2. You can see how dramatically this will start changing the way that your workers can get in and out and do the work, correctly and very, very quickly. Okay, that's why it's very important. All right. So in summary, the REA, it's like the proverbial seatbelt, or an airbag. The REA and arc-resistant switchgear go together, and that's the crux of the matter. And what we're trying to emote is that in effect, we can, from an arc mitigation standpoint, we can tie both of them together with those two products. Well, thank you very much. Appreciate it.